So the marks for the first exercise are up. You should be able to see them on Quarkus. If you see a 0, that's bad, and you should talk to me. Either you should have completed the exercise or you should talk to me. I got 1 or 2 people still in tech support for Logic 2010. If you're having technical problems with Logic 2010 and you haven't gotten in touch with me yet, like, it's almost too late. My sympathy is going to be very, very thin if it's September 24th, we're like, it's officially fall. It's gray and cold out. If you haven't sort of gotten into the flow of this yet, it's getting to be too late, yeah? I see that almost everybody sort of sorted this out. So I'm glad that we're sort of in the flow of it now. The second exercises are up. So we're into the flow now, yeah? Times for the logic lab are posted on Quarkus. They're the same as they were from this week, or sorry, from last week. So there's one today, there's one on Friday. Thinking maybe of adding one on Thursday. We'll see how well attended those sessions are. We're now getting to the point where it starts to make sense for you to kind of come into the logic lab and seek out our help for non-technical support reasons. So you'll see we're getting into the slightly hectic part of the derivations. We're adding some more connectives this week, so things are going to start to get more challenging in the pure logical sense rather than just how do I work Logic 2010 sense. So do come to those sessions, do look for extra help. Those are like the tutorials that you can show up to if you feel like it. I'm glad to see people discussing things on Quarkus, so there's a lively discussion going on the discussion board on Quarkus. If you see something there, but some of you, what I'd like to give you a heads up on, some of you are ahead of the game. So some of you are discussing derivations that we haven't learned how to do yet. So if you go on that discussion board and see like people talking about things that you've never heard of, despite having been to all the lectures and done all the exercises, that's probably what's going on. So people who have maybe taken this class before or have read ahead in the textbook are getting ahead of the workload for the semester. So if you see something and you're like, I don't know what that is even, what's going on, did I miss something? Chances are they're ahead of where we are in class, yeah? So I saw there's a discussion of a derivation that I think we've assigned this week for this week's exercises already happening on Quarkus. So don't panic if you see something that you've never heard of before being discussed on Quarkus. There is an issue about posting images. It would be really nice if we could post images of our work on Quarkus. Has anybody worked out how to, so I can do that. I've figured that out. Has anybody else got that from the student's perspective? So I don't know if this is a thing from the student's perspective or not.
Like attach the screenshot?
You can to attach a screenshot.
You attach it and then just like click on the link.
Yeah, okay, so you say attach an image and then you upload the file. You have to select the file from your hard drive and then it gives you a little link.
Yeah, there's no way to like upload it and then the image being on the post, but if you
Right.
click on the link, yeah.
Right. Okay. So the question for us is you can embed an image, but you have to click on it to see it. You have to download it to see it. The question is that inconvenient enough for us to switch to Piazza? That the main advantage of Piazza, as far as I can see, is that you can embed an image that's right in the file or right in the message. In some sense, I like that you can't see it until you've clicked on it because it's kind of spoilers. Right? So if you've given people some information about how to do the derivation and then you show them a picture of the whole thing, you've kind of given away the ending of the drama. So, okay, so do try to work out how to do this. So it's a embed image, and then on the right-hand side of the screen, there's I'll make a video. I'll make a video showing what this looks like from my perspective. But okay, so we'll continue on with the Quarkus discussion board for now. Yeah? Okay, and any course questions, anything about the mechanics of the course you want to clear up really quick? Good. So let's proceed. So we've been doing derivations. We're going to do more derivation stuff now. And I want to talk briefly. We've got enough stuff about derivations now that we can discuss derivation strategy. So far, this stuff hasn't been super relevant to you. The derivations we've been doing are relatively simple. Like, they're not that complex. Given the stuff that we'll do today, you're going to have to start thinking about your strategy for derivations. And your strategy for derivations is very similar to the strategy you should adopt in your entire life. So in your life, you should constantly be asking yourself these two questions. What have I got, and where am I trying to go? What assets have I got? What things can I use to get me towards my goals? And then what are my goals? Yeah? So these questions you should be asking yourself repeatedly throughout your derivations. And let me talk very briefly about what the answers to these questions are going to look like in a given derivation. So what you have are the following things. You have the premises. The premises are given to you as assets, as resources for you to use doing your derivation. You also have things that you've derived. So once you've derived something from the premises, you've got that too as an asset. And moving through a derivation is unlocking assets for yourself that you can use to do more stuff. Right? So the more stuff you've derived, the more assets you have to get you towards your goals. With the caveat that we'll discuss soon that you don't get every single thing that you've derived. If you're in a boxed show line, which we'll discuss this class, then you don't get to use it. So we'll talk about that little exception shortly. Okay? So basically, though, what you have are your premises and the things that you've derived from your premises. Right? And you can use those to derive things. So those are your assets. And you use those assets with the rules. So far we've introduced 4 rules. Next week we'll introduce a bunch more. We'll kind of add rules as we go along. But those rules are the sort of tools that you have to manipulate those assets. You've got the stuff in the premises, you've got the stuff on the lines, and the rules that we're allowed to use are truth-preserving rules that let you turn those assets into something new. So far, so good, yeah? This is all just sort of implicit in what we've talked about, but I want to get this really clear now before the derivations get more complex, because they will get more complex. Okay, so these are the rules we've introduced so far. They should be very familiar by now, right? So what you're looking for when you say, what can I do with what I've got, is places that you can apply the rules. And when you're looking for places to apply the rules, you have to keep parsing in mind. Okay, so that's why we're making you do these parsing questions. In some sense, every derivation contains dozens and dozens of parsing questions, right? Because these rules only apply to the main connective of the sentence. Okay, so we've got, square and circle here. Square and circle could be filled out by just P and Q, or it could be filled out by something big and complicated. So when you're learning to apply these rules, learning to identify the main connective of the sentence is crucial, because you can't apply the rule to things inside the square or things inside the circle. You can only apply it to the main connective of the sentence that you're working with. So that's why I'm making you do parsing. Parsing is the skill of identifying the main connective and knowing how you are allowed to apply the rule to use the assets that you've got to get you where you want to go. Okay, so here's an example of it going wrong. So we tried to apply modus. We say, okay, what have I got? I've got if P, then if Q, then R. So given that as a premise, and so given Q, you might be tempted to say, I know what I can do with this. I can do a modus ponens on that if Q, then R. I can use Q and use if Q, then R to get R out of that. But you're not allowed to do that. You're not allowed to do that because you can only apply this rule, modus ponens, to the main connective of that sentence. And what's the main connective of that sentence? The if P then something, right? The first if then statement, the first conditional is the main connective of that sentence. You're not allowed to go inside the parts of the sentence and apply the rules to the parts. Yeah?
Could you say if P then R then, or?
No. You can't say if P then R. Yeah, because that's once again going inside one of the parts. Let's think of an example. So you say, if I'm depressed, then if it's raining, then I'm happy. And you say, I'm depressed, therefore I'm happy. That doesn't work, right, as an inference. So the if P, what that first sentence there says is, if P is true, then this conditional is true. And if you don't have that the conditional is true, then you can't use it in a modus ponens. Right? So this is how parsing is connected to the derivation stuff. It's also going to be connected to our symbolization and our truth tables. So parsing is throughout all of the skills that you're going to be required to do. Identifying the main connective tells you how you're allowed to apply the rules. Here's one that actually works. Because the main connective is that first conditional, if you've got if P, then blah, 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 and you've got P, then you get blah, 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 right? Because that's the main connective of the sentence. The circle, so in the rule here, the circle is if Q, then R, right? So the circle can represent as complex a sentence as you want. And they'll get fairly complex. Like it'll be big, chunky, complex things. And you say, if P, then this big, chunky, complex thing. I've got P, so I get this big, chunky, complex thing. OK? OK, so this is using your assets via the rules. But you got to be really picky about how you're using the assets that you've got. You have to be really careful about where you're allowed to apply the rules. OK? Here's another one. Modus tollens. Again, we're being really picky here. Really, really picky. You can make this inference in one extra step. You get one extra step. So it looks like, modus tollens. Look, the negation of the second thing gives you the negation of the first thing. Modus tollens, perfectly good. Why is this wrong? Yeah? You got to double negate because the thing in the circle here is not R, right? And not R is the negation of that. Yeah? This is why can't we just, it makes sense. Why can't we just, no, because you used a tiny bit of insight and imagination there. And what we're doing is ruling out insight and imagination. You are not allowed to say, oh, well, it's just obvious to me. Right? That's the spark of human intelligence and creativity, which we are stamping out here. We're saying, what can we do without that? Right? So by the way, this is why formal logic is so bad for building artificial intelligence, because you don't end up being very intelligent if you stamp out the spark of human creativity and insight. We tried it for like 30 years and it didn't work at all. Right? You actually need that stuff to be a human. But for this class, we're saying, no. Don't do it because it's obvious. Do it because it follows the rules precisely. Right? So when we're parsing this sentence, the main connective is the conditional. And the whole thing that comes after the conditional is what goes in that circle. So you need the negation of whatever's in that circle, which is not R, not R. That was a bad sentence, but hopefully it's clear enough. So if you have this, that's fine. So if you have if not T, then not R, not R, and you might be tempted to get not T out of that. I think Logic 2010 lets you choose which version you want, but you get not T. Okay? Okay. So, to come back to this derivation strategy stuff. When you look at the premises, so this is the forward-looking. So there's two ways of dealing with the derivation. You've got a forward-looking way and a backwards-looking way. And you're going to have to kind of switch between them. You're going to have to be able to dynamically flip between these two perspectives and to try to meet somewhere in the middle. In really simple derivations like this, you can really just take one perspective and get all the way to the end. But once it gets more complex, you're going to have to do a little bit of both. So far, let's try the what you've got strategy. So what have I got here? Actually, so I'll do this in more detail. And where you're going, in addition to asking what I've got, you can start from the end. Start from the end and work backwards. So let me show you that with this particular derivation. Okay, so here's that derivation once more. Now, let's do the forward-looking strategy. So ignore where you're trying to get. Forget about where you're trying to get. Just think about what you've got. And so far what you've got are just these premises, right? So you look at what you've got and think about what you can do with it. So which rules can you apply given these premises? Okay, well, can't really do much with this. Like if I had the negation of this part, then I could do something with that. Or if I had this, then I could do something with that. But I haven't got either of those yet, right? Okay, what about these two? Well, if I had the negation of this, I can get the negation of this. Okay, so working this way, we can say, look, this Q is going to give me not Q, which is the negation of this. So if I double negate this Q, I can get the negation of this, which then gives me this, or the negation of this, right? And then if I've got not P, that'll give me P, and then I can use it here to give me this. And then if I've got P, then I can get this. So I can get if Q, then not R. And lo and behold, I've got Q, so I can get not R. Oh, hey, just looking at what I've got, I ended up with what I was going for, right? So we did that entire thing step by step in a forward-looking way, just saying, okay, what have I got and what can I do with it? This is like not thinking about how you want your life to go and just saying, well, I'm pretty good at, video games. Maybe I'll just do that 80 hours a week and become a professional esport player, and then you became a millionaire. Without even considering what your goal is, you just said, okay, what assets have I got and what can I do with them? Not a great life strategy in total. You also want to be doing the opposite, right? You also want to be asking yourself, okay, where am I trying to get? What is the thing that I'm trying to get out of this? So not R. Okay, not R. So how do I get not R? From this mess of stuff, what have I got? Well, the only place that R shows up is in this one. Okay, so not R, right? If I can get Q, then I can get not R, and I'm done. Okay, so working backwards, I say, okay, if I want not R, I should get Q. But hang on, I can't get this whole thing without getting P, right? So, okay, so I need to get this whole conditional in order to get P. So where do I get P from? Well, not P. Okay, that looks hopeful, right? So I want this conditional, so I want P. So then okay, where else does P show up? Oh, it shows up here. All right, so not P. Okay, cool. So I'm going to try to get somehow, look, I'm going to try to get P, something about P, right? I need P to get this thing, to get this thing. Okay, so not P. All right, well, how do I get not P? Well, something to do with not Q. Oh, well, I can just double negate this, and I can work backwards. So then I just did the whole thing backwards, starting from where I'm trying to get, and just working backwards step by step through the whole derivation, saying, okay, well, what do I do to get this? What do I do to get that? Let me just really quickly show you the end result, which should be identical either way. Write my show line, not R. Right, and how do we say this is good? So going forward is easy as actually writing it out because we have to write this thing out. So given premise 3 and premise 2, so we say premise 3, we had to double negate it, of course, and then premise 2, PR3, PR2, modus tollens, right? So premise 3 double negated, premise 2 modus tollens gives us not P, good. And then we can say line 2, double negation, because we can knock those double negations off. Premise 1, modus ponens, and that gives me, shout it out, if Q then not R. I heard some careful mumbling. Okay. And now, because I've got Q, I can use this line, so line 3, premise 3, modus ponens, to get not R, and that's it. Direct derivation. Cancel the show line, box it off, I'm done. Yeah?
Can you put the double negation in the justification, or do you want us to show that as another step?
So you're absolutely allowed to compress like this. So the answer is either way is perfectly fine. So what I've done on the screen here is compress things quite a bit. I could have stretched this out in a bunch more lines. They are logically equivalent, which means to us that they are exactly as good as each other. Yeah. So if you want to do double negation, if you wanted to do on line 3 just 2 double negation, and then you get not R, that would have been totally fine. Your lines would have ended up differently, but the people marking your tests will be able to say, oh yeah, that all works, that all works. So the very first derivations I showed you, I kind of did it very carefully, line by line by line. Now I'm kind of compressing things a little, but they're both exactly as good as each other. Yeah? Okay. Is the point that I'm trying to make fairly clear, which is that you can think through, so this is just derivation strategy, thinking through how you're going to approach a derivation. And I showed you the 2 ways that you can do it. You can start from what you've got. Okay, so look at what you got and think, what rules apply to these things? What can I tease out of this just given my premises and my rules? That's one strategy. And then the other strategy is, where am I trying to get? And now, how do I get there? So what do I need in order to get where I'm going? You need both of these strategies. You can't just rest on that. You cannot just say, okay, what have I got and what can I do with it, and just mess around. Because, for one thing, I'm at some point going to ask you to derive a theorem. And a theorem is a proof that starts with no premises. To derive a theorem, I give you no premises and say, just derive this thing. And you can do this. This is a quite possible thing to do, but you have to do the backwards strategy. Okay, and how do I, no, that doesn't work. Everything that I've taught you so far, that makes no sense. But today, I'm going to show you how that could make sense. So the tools that we'll learn today make it possible to derive something from nothing. Okay? Okay. So, derivation strategy. We will come back to this. This is just by way of kind of gentle introduction to the very idea that you're going to have to strategize here. Okay. Okay. So if that's okay, I mean, partly the significance of what I just told you isn't going to be totally obvious until you get deeper into this derivation stuff. So let's go deeper into the derivation stuff such that that strategy stuff will be more important to you. So let's talk about conditional and indirect derivations. Remember how I've been asking you to write DD, direct derivation, at the end of all your derivations? Why? Why didn't you just say derivation? Or why didn't you just say QED, like old-timey philosophers did? That's because there are at least 2 others. We're going to learn these 2 today and one much later on. So there's several types of derivation that you can use. So we're going to learn the other 2 today, or 2 more of them today, indirect and conditional derivations. Okay, so these are different ways of doing a derivation than direct derivation. So the direct derivation just goes straight from the premises to the conclusion. It says, I'm just going to apply my rules to my premises, boop, 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 I get to the conclusion, the end. Yeah? It's the simplest form of derivation. It's the most straightforward. It's the one that's most intuitive, maybe. But it's not always going to work. It is not always going to work. So some things that it's fairly obvious that you should be able to prove, you can't prove just using direct derivation. So if you just try to use direct derivation, you will sometimes, actually very often, from here on in, get stuck. So we need ways of getting you unstuck. So here's a Here's an argument that looks really, really valid. It is valid. That's why it looks valid. If it rains, the picnic will be canceled. If the picnic is canceled, then I get to eat all these sandwiches. And then you derive from that the conditional that if it rains, I get to eat all these sandwiches. Yeah? That looks right? That looks like it should be a valid argument. If the first two things are true, the third thing's got to be true, right? Just intuitively. But you cannot derive this with the skills that we've talked about so far. So we'll quickly symbolize it. R is it rains, P is the picnic will be canceled, and S is I get to eat all these sandwiches. So if R then P, if P then S, if R then S. Does that sound okay as a symbolization? Any worries about that? Okay. So now we're going to try to derive if R then P, if P then S, then if R then S. Okay. So as always, we begin with a show line. Line 1. Show if R then S. Okay. Now given the 4 rules that you've got so far, what do? You can't modus ponens anything. You can't modus tollens anything because you don't have any antecedents and you don't have any consequence. You could repeat. You could say premise 1, repeat, 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 repeat. You could double negate the heck out of these things. You could add so many negations, as many as you want. This will not get you to your goals, right? Neither of those moves. So you can't use modus tollens, you can't use modus ponens, and repeat and double negation will get you nowhere. What do? Well, you do this next thing. You do this conditional derivation. So what we're going to allow ourselves to do is the following. We're going to say, assume for conditional derivation R. And then we're going to show, we'll write ourselves another show line, S. Okay. Why was it okay for us to assume that? Sorry, yeah.
Sorry, I have a question.
Yeah.
In the textbook, when it does conditional or assuming conditionals, it doesn't have a show line for that conditional. So it would just, like, I don't know if it's good, but I would continue it without that show S. Can I do that?
You should do that show S. Do that show S. Yeah. Do that show S at least partly because Logic 2010 needs you to do that show S. The other reason is, as we get into more complex stuff, you'll see why having that show line is useful to you. The reason why it could be, just to foreshadow a little, this won't make sense yet, it's useful to have that show line because if you don't have anything else you can do here, you can start an indirect derivation using that show line. So it's a useful, show lines, we'll see if we have time today, we'll see how show lines can actually be a kind of asset. Now, what we just did was assume that the antecedent is true. So assuming that R is true, and now we're trying to show the consequent, right? So you say, well, just give me the antecedent. I'm going to assume it for this derivation, and now see if I can get S out of that, right? And if you can get S by assuming R, then what you've shown is that if R is true, then S is going to be true. And you've shown that that conditional has got to come out as true, right? Okay. So on line 4, now we've got, so because we've assumed this for conditional derivation, now we've got it as an asset, right? We've got this line that we can use to do stuff with. You're going to have to do the following. So you're going to have to bring it into this. So what I've done is started a subderivation. Right? This is a derivation within a derivation. I've written myself another show line. So when you start a subderivation, if you want to use something on a higher up line, you have to say to repeat. Why do we have that repeat rule? That's so you can bring things into a subderivation. So we say to repeat, and we can use premise 1 here, premise 1, and do a modus ponens, right? And that gives us P. Now we've got P, we can use it to do stuff. We can use it with this premise. So line 4, premise 2, modus ponens. Now we've got S. And that was the thing. Always keep in mind what your goals were. Again, in your life, you should keep in mind what your goals were so that you don't end up with like a beautiful house and a family and feel completely unsatisfied. Right? I often like to remember what 14-year-old me thought a great life would be and think, oh my God, 14-year-old me would think this is amazing. Okay, so this is like, oh yeah, that's the thing I was trying to show all along. So very good. So now we've got on line 5, we don't write direct derivation because we assume this for a conditional derivation. But we 5, conditional derivation. So we've shown S, cancel, and box. And now that we've shown S, so now we've got line 3 as an asset. Once you've completed the subderivation, you've shown the thing that you set out to show, now you can use that thing because you've shown it, right? You can use that line as an asset. So we've got S. So we set out to show S. Now we've got S. So that means that on line, wait, is this a, no, this was a direct, I'm sorry. This was a direct derivation. Now we've got our conditional derivation. Now we've got on line 3, we did the conditional derivation. Cancel and box. Okay. Sorry. So this is a direct derivation because I didn't do assume. So when you start this subderivation, you assume for conditional derivation. When I started this subderivation, I just did the normal thing, right? I just did a direct derivation. That's why this is 5. On line 5, I have a direct derivation of the thing I was going for. Cancel and box. And now on line 3, I have the thing that I was trying to get because I wanted to get, assuming R, can I get S? Well, yes, I can. Therefore, you've shown that if R is true, S must be true as well. Okay? That was a conditional derivation. And our first subderivation, that was the first time we ever had a derivation within a derivation. We will see a lot of this as we go along. Questions about that? Yeah.
So we've shown that if R is true, then S will be true.
Yeah.
But the if conditional statement has a variety of different inputs and outputs, right? Do we have to now show that if R is false, then S must be, or then do we have to show that if R is false, S can be true or false?
No, you don't. Okay, so, and here's why. It's a good question. You're like, oh, well, you know, if R is true, then you get S. But what about if R is false? If R is false, then the conditional comes out as true, right? So if the antecedent, remember the truth table for the conditional, if the antecedent is false, then the whole thing comes out as automatically true. And what we're trying to show in this derivation, the goal of this derivation was to show that given these two premises, the conclusion must be true. So if you say, in the case where R happens to be false, the conclusion has to be true. Yeah? So we've shown that you can't end up, given that those two premises are true, you cannot end up in a situation where the conclusion is false. Yeah?
Why is that a rule that if the antecedent is false, that the consequent has to be true? If given in the real world, that's certainly not the case.
Because logic is imprecise. And furthermore, what I'm showing you right now is the simplest form of logic that we've got. So There are more complex ways of saying what the if-then statement means, but they go way, way beyond the level of this course. So I'm not teaching those to you. They go into things like, in the nearest possible world where P is true, is S true now? And that's gets you into like which worlds are possible. That gets you into, it's no longer truth functional as well. So these conditionals, these rules are all truth functional, which means given one specific set of inputs, it always gives the same output. So given true, true, it always says true. Given false, true, it always says false, and so on. So the actual if-then statement in English is not truth functional in that way, but the system we're dealing with has got to be truth functional. Yeah? Yeah?
Should you not be including like the 5 direct derivation and 3 conditional derivation? Should you not be including those in the boxes? So for like the show S, the smaller box, should that not include 5?
Yeah, I mean, I don't care much about that. Okay. Well, so is the question, shouldn't this line extend down to the 5 dd?
Yeah, and same with the other one for like that, yeah.
I don't care much about that. Okay. Yeah, I don't think that there's a strict convention about whether it needs to be at the top of this line or the bottom of this line. If you drew it in the middle, that would be fine too. I hope it's starting to become clear why you wouldn't want to, so as we get into more subderivations, why you wouldn't want to draw it around this. So we discussed briefly last time like this, because we'll have a bunch of derivations embedded within derivations and you start to mess up your ability to read this. But yeah, so long as you've boxed in all of the lines that you've used, I think it's fine, whether you do it at the top or the bottom of the line. Yeah? Yeah?
Could you quickly go over what 2R means again?
To repeat. Yeah. So on this line, no, that should be a, to repeat, that should be an R. This should be an R. That's 2 mistakes I've made this derivation. But nobody called me out on it, so it seems to have been okay.
It should be a P, because you compressed it. So it's R and R.
Oh, right. No, you're right. You're right.
P, so P.
Thank you. So I made a mistake about my mistake. Okay. So I'm so eager to find ways in which I've made errors. Okay, so to repeat says the following. So suppose let's back all the way up through this. What would that have done if I hadn't? So okay, we're back to, okay, I want to show this thing. I'm going to assume R for conditional derivation. I'm going to show S. Okay, I'm fresh, I'm young, I'm eager. So what I want is to use R to modus ponens this, right? But once you're inside a subderivation, you have to bring whatever assets. It's like you make up a little mini world for yourself in this subderivation. You'll see why when we do indirect derivation in a little bit. You're creating a little mini world for yourself in this subderivation. And if you want to use things in this little mini world, you have to bring them into the mini world. Right? So you're not allowed to just grab resources at random. Within a subderivation, you're allowed to grab the premises because these are always going to be assumed to be true. But you need to, if you're going to use one of the lines, so if I just said to repeat, what that would do is just bring R into my subderivation. And then I can use it on subsequent lines. So if I say premise 1, modus ponens, now I get premise 1 and line 4, right? So now just repeating it, it's just sort of brought this asset into this subderivation. Now, that sounds trivial, but once you've got, so for example, suppose we've completed this subderivation, and I want to use P for something. Because this is boxed in, this is no longer, P is no longer an asset that I can just use on, so if I said, suppose this is all boxed in, if I then said premise 2, line 5 modus ponens, that wouldn't be allowed because this is sort of like you said, okay, imagine for a second the universe is like this in your subderivation. You create a little mini world for yourself in your subderivation. And then you say, okay, given that that is true in my little mini world, I'm going to export that to your no longer mini world. That's invalid. This is getting metaphysical. It'll be clearer when we do indirect derivation why you have to do this repeat. Yeah?
Yeah, I just want to say that. Why not just like write line 2 instead of writing line 2?
I don't know. I don't know why that's the convention, but that is the convention. So, yeah. Yeah. I don't have a good reason why that's the convention, but that's the convention we'll require. Yeah.
I think the textbook uses like a slightly different method for calling on the premises. Do you prefer if we like write the premises in the derivation itself, or just call on the premises like with numbers from?
I see. I see. Yeah. So in the textbook, yeah, they sometimes instead of just saying, instead of writing premise 1 modus ponens, they'll actually write in. They'll say, is this what you're thinking of? They'll have premise 1 and R, then P. Yeah. Oh yeah, they just say premise. So you can just cite them. That's fine. Do number them, but you can just cite them. Yeah. You're allowed to do this, of course. If you say premise 1, R, then P, and you want to do just every single step, and now you say line 4, line 5, modus ponens, give me P, that's fine. That's fine. It's equivalent for our purposes. Okay? Okay. Okay, that's probably enough of this particular example. So in any case, basically in any case where you're trying to show a conditional, you're going to want to start a conditional derivation. So this is kind of an automatic move. It's a proof that if the antecedent is true, then the consequent will be true. There's kind of no other way to, well, unless you've got the conditional in one of the premises, it's really hard to show a premise show a conditional except using a conditional derivation. So to repeat, after a show line that contains a conditional as the major connective, you can't just show so yeah, these got to be the major connective of that sentence. You want to show this sentence. If the major connective of that sentence is a conditional, then you can assume the antecedent. You say assume the antecedent, and for conditional derivation, assume CD, and then show the consequent. This must come right after the show line. You can't just start these things in the middle of a derivation. It has to come right after a show line. Okay? Okay. Then I was going to go into my examples. Let's do one more example of a conditional derivation, and then I'll give you a break, and we'll do indirect derivation. So this is, I want to assure you, the exact same derivation as we just saw, just with slightly more complicated bits. Right? So if you remember how to do that last derivation, you know how to do this derivation. I see some of you working on this. That's a great idea, actually. To bring pencil and paper and to do these along with me is a really good idea. If you're just watching this on YouTube, I see the class is not full. So if you're just watching this on YouTube, this would be a great time to pause and just try to do it yourself. Okay. None of you in front of me have that option. You cannot stop. If you can stop time, now would be a good time. I won't notice. All right. So we're going to show this conclusion. We're going to show if not V, then if X, then Y. Okay. And I told you before, I just told you this is the exact same derivation. So the major connective of this is this conditional, right? if it looked like this, then you can't do a conditional derivation. Because if I put those brackets in, then that's now the major connective, right? So good thing for us, that's not what we're doing. We're doing this, where this arrow is the major connective. And so we assume for conditional derivation, not V. Assume for conditional derivation. And now we want to show this conditional. Okay. Now, usually if I'm doing something like this, I'll want to, so I'm going to show this conditional. As a matter of fact, I don't need to do another show line here. I could do another, okay, let's do it. Let's do it and see what happens. So because I'm going to show another conditional, I can assume for conditional derivation x and do yet another subderivation, show y. Yeah?
Do we have to repeat the line number like it says 2, 2?
Oh,
Or not?
no. I would prefer if you didn't do that at all. Yeah, no, that's very much an error. Oh, that's ugly. Okay. Okay. 4, 5. I think, in fact, I didn't have to do this second one, but let's do it anyway. So show y. Okay. So now I've got these as assets. I've got x and I've got not v. I didn't actually, you know what? Let's make this simpler for ourselves, and I'm not going to do this second show line. Okay. Just to show you that this is, in fact, the exact same derivation that we just did. So we assumed for conditional derivation y, and now we want to, sorry, we're not even going to do this. Okay. Okay. Now we want to show if x then y. Okay. It's the exact same derivation. We have the resources available to do this right now because we've got not v, right? So we say line 2, repeat to get it into our subderivation, and then premise 2, modus ponens. And that gives us t. And now, on line whatever this is, 5, I suppose, we can use this asset and this premise. So we say line 4, premise 1, modus ponens, and we get if x, then y, which is the thing that we were trying to show. So we've got, this was a direct derivation, so on line 5, we did a direct derivation, cancel, and box. I suppose I want you to write the bottom line a bit higher up so that you have space for the next line below it, if that's okay. It's legibility questions. So we've shown if x then y on the assumption that v, we've assumed not v, sorry, we assumed not v. We've shown that if you assume not v, you get if x then y. So we've done the thing that we were trying to show, right? So we've shown the consequent of this thing by assuming the antecedent, which shows that on line 3, so on the show line where we accomplished that, we've done our conditional derivation. We can cancel and box. That was kind of a bad example because the automatic move should have been to start another conditional derivation, but anyway. Do you see how that's the same derivation as before? So just to show you the comparison. So we just assumed the antecedent. We tried to show the consequent. We used the thing that we assumed and one of the premises and got the thing that we're looking for. Okay. Okay, let's take a 10-minute break. We'll come back and do indirect derivations. So come back at 11:10. So that was the basic idea of conditional derivations, clumsily presented. It should become clear as you practice them what exactly goes on with these conditional derivations. So the practice examples for this week, the exercises for this week involve a bunch of conditional derivations and a bunch of indirect derivations, and one or two, I believe, that involve both conditional and indirect derivations. So let's do indirect derivations now. We'll have both sides of this, and then we can put them together into a kind of dynamic, unified whole. So indirect derivations, a whole nother kind of derivation where you derive something by assuming the opposite and then from the opposite deriving a contradiction. So a contradiction is automatically false, right? If I say P and not P, you know that that whole sentence is false, for sure. You know that a contradiction is false, which means anything that's, and in our system, if it's not false, you know it's true. So if you want to prove something is true, you assume the opposite of it, derive a contradiction, and that shows you that it must be true. It's like, if you're from philosophy, it's like a reductio ad absurdum. You say, okay, let's assume that that thing is true for a second, and then you derive something ridiculous from it, and deriving something ridiculous from it shows you that that assumption must have been wrong. That assumption must have been false. Okay? So, immediately after a show line, you can use the following rule. Assume for indirect derivation. Must be immediately after. You can't just sort of assume things for indirect derivation whenever you want. Has to be right after a show line. Okay. So let's do an example. Come now. Okay. So as always, we say, show the conclusion, show Q. Okay, now, given the tools that I've shown you so far, there's nothing you can do here. You got nothing. You got nothing. You've got no premises that are the antecedent of anything. You've got no premises that are the consequent of anything. You've just got a couple of conditionals. And again, you can't use modus ponens. You can't use modus tollens. You can double negate and repeat all you want. It'll never get you closer to deriving Q. So you need to do something else. And furthermore, Q is not a conditional. So you can't even do this assume for conditional derivation thing that was so helpful to us. So we need something else. We need another move here to get us unstuck, because right now we are completely stuck. So what we're going to do is assume for, oh, by the way, I think I've been using capitals and lowercase letters interchangeably. That's fine. You can write these in capitals or lowercase as you please. Okay, so we're going to assume for indirect derivation, not Q. Okay, so now we've started an indirect derivation. This show line has begun to be an indirect derivation. And we're saying, okay. I don't know how to, given what I've got, I don't know how to show Q is true. So what I'm going to do is assume that Q is false and try to do something with it. Try to do something with that assumption and try to generate a contradiction somehow. So now when you're doing an indirect derivation, what you're trying to do is to get two lines that say the exact opposite of each other. And if you've got two lines that are the exact opposite of each other, you've derived a contradiction, which means that that assumption that you made has to be false, which means the negation of that assumption has to be true. Okay. So given that we've assumed this for indirect derivation, now I've got a thing, right? Now I've got a thing I can use. So this is an asset for me now. Line 2 is an asset that I can use applying my rules and applying it to these premises. So what is this asset good for? Okay, not Q. Well, that's the negation of these two consequents, so good. So I can say premise 1, line 2, modus tollens, and that'll give me V. Okay, what else can I do? Well, it's also the negation of this thing. So premise 2, line 2, modus tollens, giving me not V. And now I've got V and not V. Well, that can't be right. Yeah.
Do you just show the double negative for one of those steps?
Oh, should it be not V? No, I don't. I think when you're using modus tollens, you can just go to not V. Yeah.
Couldn't you also show the same thing from line 3 by saying premise 1, line 3, both opponents? Couldn't that show the same thing? Oh, wait, never mind.
Okay. 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 Yeah. Yeah.
Would it be the other way around? Like, isn't premise 1 and line 2 modus tollens?
Yeah.
And
Boy, they sure should be. So this should be error. Thank you. So premise 1, line 2. So what do I get? From premise 1 and line 2, negation of this, that should be not V. When I practice these at home in my comfortable living room, it works every time. Yeah.
Sorry, but yeah, so if you did have V, right?
Yeah.
At one point you did, didn't you?
Yeah, so we're going to do premise 2, line 2, modus tollens, and that'll give us V.
Okay, never mind then.
Yeah. Okay. And for purposes of demonstration, so now we've got on line 3 and line 4, we've generated our contradiction. We've generated something that cannot those two lines cannot possibly be true at the same time, and yet we've derived them using truth-preserving rules from our premises. So that means that on line 3 and line 4, we've done our indirect derivation. And we can cancel and box. Okay? Yeah?
For line 4, should we get not V instead of
I think it's okay to do. You could do not V. You could just do V for modus tollens. So logic 20. I'm trying to match what logic 2010 does, so I'm not presenting you with a confusing set of rules. Logic 2010, when you do modus tollens, offers you the option of one or the other. So I'm going to offer you the option of one or the other. That's basically, so there's so many things in this course where you're like, why are you doing it like this? It is kind of because I said so or because that's the convention. And I'm trying to match the conventions of logic 2010 so you have a consistent set of conventions. Is that okay? Yeah. Yeah.
Do we need to write the and, like double negation after empty, we just want to write?
We were just discussing that.
Do we have to write
No, the answer was no in this case.
If you show the double negation, do you have to do the DN? Like if you do it, negation.
So in this case, so if you done, yeah, so if you derive, so if this was the way you'd written it, no, you don't have to do a double negation because this is still the negation of this. So not V is the negation of not V, so you can just write this out. Yeah.
It's just not entirely clear to me what exactly the significance of having these two contradictory
Yeah.
statements
Good.
are.
So this is the crucial thing. This is important. So, okay. What we've done in any indirect derivation, what you're doing is making an assumption and trying to generate a contradiction from that assumption to show that that assumption has to be false. So what we want here is to show that Q is true, right? That's the goal of this derivation. Show that Q is true. So to get to our goal, what we first do is assume the opposite of that goal. And then we say, okay, what follows? If I assume the opposite of this, now what follows? What happens when I assume the opposite of Q? And if you get a contradiction from that assumption, then you know that that assumption must have been false, which means the negation of that assumption must be true.
Okay, so by creating this contradiction, you know that logically if your initial assumption was in fact true, then the whole argument is.
So it depends what you mean by initial assumption. So we're trying to show Q. The assumption is that Q is false, and then that gets us into this clearly impossible situation. And because you've gotten into a clearly impossible situation, that means that not Q must be false. And that means if not Q is false, that means that Q has to be true. So we've shown that Q has to be true by assuming the opposite and deriving a contradiction. Yeah?
If you have, if on premise 2, if not V, then Q, and
Yeah.
you already have on line 3, not V, can't you assume that Q is, can't you get Q from it?
Good, good. So yes, you could. Yes, you could. And we'll talk about this very briefly. So we're gonna talk about mixed derivations, but here's a thing that you could have done. So we've assumed not Q, we've derived not V, but can't we just do, so the question was, can't we just do the following? Can't we say premise 2, line 3, modus ponens, and get Q? Oh, and that's the thing we're trying to get. Oh, okay. Well, then we're done. 5, direct derivation. Box and cancel. So that's what's called a mixed derivation. It's a derivation where you start one kind of derivation and end with the other. And I'm going to hang on just 1 second, and we'll show you why that's a legitimate. I'm going to talk at some length at why that's a legitimate thing to do. That's a legitimate thing to do. In our system, that's perfectly fine. You can see why that's perfectly fine. I mean, just really briefly. So we've got, this is a perfectly fine thing to have derived. Now, we kind of just sort of skipped a step. When we say line 4 direct derivation, we kind of just skipped a step because we've derived a contradiction, haven't we? So we could have also said, this would also have been fine, 2, 3, indirect derivation. Because on line 2, we've got not Q. On line 4, we've got Q. So that's our contradiction as well. We could have gone like that. Now, I wanted to show you this way because I wanted it to be clear. So we get not V from premise 2, line 2, modus tollens, and then 3, 4, indirect derivation. I wanted it to be clear that you don't have to derive the opposite of this. You don't have to derive the opposite of your thing that you assumed. If you derive any contradiction, that's good enough to show that your assumption was false. Yeah? Okay. Do I have another example here? I think I have another example for us to do. Right. Yeah. So. Oh, I think this was a more complicated example. Do we want to do this now? Yeah, this was a more complicated example. We'll come back to this. So I think this is going to end up being a mixed derivation. So let's come back to this in a sec. Okay. Okay. So that was the very basics of conditional derivation, the very basics of indirect derivation. And hopefully it's fairly clear why both of those are, hopefully it becomes clear why both of those are legitimate ways of doing a derivation. If you assume one thing and get the other, then you have the conditional if this, then that. If you assume the opposite of something and derive a contradiction, then you know that that thing is true because the opposite generates something impossible. When you're doing your derivations, you get kind of these automatic moves. using these types of derivation, these moves become automatic. So writing these show lines becomes something you don't really have to think about. So if you have a show line that says is a conditional, is the major connective is a conditional, then you just start a conditional derivation. If you're trying to show something that's not a conditional, you're pretty much always going to start an indirect derivation. Because you're giving yourself assets that you can't get yourself, basically you do these as automatic moves because you can't get in trouble by making them. Right? You can't screw it up by starting a conditional derivation to try to show a conditional, and you can't screw it up by starting an indirect derivation to show something that's not a conditional. Yeah? Okay. Subderivations. Now we're going to mix and match these two types. We've got three types of derivations on the table now, right? We've got direct derivations, conditional derivations, indirect derivations. For a bunch of the problems that you're going to face from here on in, you're going to have to use several types of these, right? You're going to have to use them in combination to get where you're going, right? So there's subderivations within subderivations. And this is where the repeat stuff becomes relevant, and this is where you have to know the difference between an available line and an unavailable line. So this is a mixed derivation, or sorry, this is one derivation inside another derivation. You start a conditional derivation, and halfway through you find yourself starting an indirect derivation. You can have the opposite of, well, you can start off an indirect derivation, and halfway through you're like, oh, now I need to start a conditional derivation. These are both completely fine. Okay. But now you have to understand the idea of available lines. Previously, this wasn't relevant to us. Now it's become relevant. Now you have to know which lines are available for use and which lines are not. So it's fairly simple which lines are available and which lines aren't. When you close off a subderivation, when you cancel the show line and box it in, now you can't use the contents of that subderivation anymore, but you can use the show line. That's basically what makes something available. So suppose we've got a big derivation, and then we start a subderivation. We're going to show Q. You've assumed not Q for indirect. You've shown that there's a contradiction somehow. Now, not Q is no longer available. That line 6, you can't use it somewhere else, right? You can use line 5, however. Now you've got Q. And this should make intuitive sense. This should make intuitive sense. So if you say, assume for a second that I have $1 million. Now, would I be wearing these clothes if I had $1 million? It's a contradiction. Therefore, I must not have $1 million. Okay? Now, you can't go on to say, and because I have $1 million, blah, 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 blah. Right? So you can't use that assumption for reductio. You've assumed something that you think is not true to derive a contradiction. You can't then use that assumption to show other things, right? That's why you got to keep it in the subderivation, right? You create a little mini world. You say, imagine for a second that I'm a millionaire, right? You imagine that, and then you derive a contradiction. So you can't use the things within that little mini universe outside the little mini universe, right? However, you can use the thing that you were trying to show. So if I'm trying to show that I don't have $1 million, and I'm like, look at my winner's outfit, then you can say like, yes, therefore I don't have $1 million, and you can use that to show other things, right? Okay. That's why you can't just grab stuff from inside a subderivation that's been closed off. But you can use the show line. So once you finish the show line, once you finish the subderivation, the show line is now one of your assets. You've shown it, you can use it. And this is why, again, why the repeat rule is relevant. Now we're going to use that repeat line to bring stuff into a subderivation. And you can only use the repeat line on an available line. An available line is a line that's above you in the derivation, and it's a line that you haven't boxed off yet, right? Okay. So here's a derivation. We've got, on line 3, we've got x. We start a subderivation. You want to bring x into that subderivation using repeat. And 3's got to be available. That's the only rule. Okay? Logic 2010 will impose this on you, so you'll get this in a kind of intuitive way. Okay. So, mixed derivations. Actually, now I think we can do this example that I was putting off this example. Let's do this example of what I think is going to be, this is not a mixed derivation, but it's a derivation where we'll need both conditional derivation and indirect derivation. I believe, if I've written down the right one. Okay, so, as always, we're going to show the thing to be shown. Not P, then not Y. Okay. Now, finish this off. Yeah. Okay, so automatic moves. Automatic moves. I just wrote that I want to show a conditional. So automatically, without having to think about it, I know I'm going to do a conditional derivation. So I'm going to assume for conditional derivation that x is true, and then I'm going to show that if not p, then not y. I got a few people asking about the difference between the textbook and how I've been doing it. Do you have to write this show line? So in the textbook, they don't always write this show line, and they don't always write this show line when it's the whole thing is a conditional derivation. I'm going to recommend that you always write it, because you don't ever get in trouble by writing it, but you might get in trouble by not writing it. So the more we can make automatic here, the better off we are, right? So you want to minimize the parts that you have to think hard about. This is a part you don't have to think about. Just write the show line. Yeah? Okay. Okay. Now, I've said I want to show this thing. Well, what is this thing? That's a conditional. So I want to, for the sake of a conditional derivation, I want to assume the antecedent. I'm going to assume this for conditional derivation and show the consequent, not y. Okay. So I'm 5 lines in, and I haven't, a single thought has not passed through my head. I have not thought about anything. I haven't looked at the conclusion I'm trying to get. I haven't looked at the assets I'm trying to get. All I've done is say, okay, I'm trying to show a conditional, so I start a conditional derivation. Now I'm trying to show another conditional. Now I'm going to start another conditional derivation. Those are all automatic moves that you don't really think about. But nonetheless, look what I've got. I've got at least 2 assets here, right? I've got x and I've got not p that I've sort of unlocked just by doing these automatic moves. I can bring these down into my subderivations. Okay, I got one more automatic move here that will unlock yet another thing for me. So now I've written a show line, show not y, and it's not a conditional. I'm going to kind of automatically assume for indirect derivation y. Right? So now I've started an indirect derivation, and I've got yet another line that I can use here. Right? Okay, all that was automatic. All that was automatic. Just what am I trying to show? Okay, well then I'm going to do my conditional derivation, if it's a conditional. What am I trying to show? It's not a conditional? All right, I'm going to start an indirect derivation. And from having really not much, like I've got 2 big weird conditionals as my premises, but now I've got x, I've got not p, and I've got y to work with. Right? So just doing these automatic moves, I've unlocked a bunch of assets for myself that I can use to interact with my premises now to try to get me to the conclusion. Okay. So what have I got? I've got x, I've got not p, I've got y. I take a look at my premises. Okay, well, x is pretty useful here, right? X gives me this, and x also gives me this. So let's do those. So I want to say line 2, repeat, to bring this x down into the subderivation, right? So I've started this subderivation. I want x in it. It's available because it's not boxed off, right? It's not part of a subderivation that I've finished. So I can use x, I can bring it down here to repeat. I'll just do this actually. So x and premise 1, modus ponens, and that gives me if y and z. Let's do the exact same thing with premise 2. 2, repeat. Premise 2, modus ponens, and that gives me if z and p. Great. Now, so far, all I've done is my automatic moves. Okay, I know which kind of derivations to start just by what kind of thing I'm trying to show. And now I'm just doing the forward-looking. So remember the forward-looking, backward-looking strategies? Right now I'm just doing the forward-looking strategy. Like, what have I got and what can I do with it? Trying to unlock some resources for myself. So, okay, here's some resources that I've unlocked for myself. I got this. I got 6, 7, and 8. Well, look at this. What can I do with 6, 7, 8? I can do line 6 and line 7. Nice modus ponens. Give myself z. Cool. Now I've got another resource, so I can use line 8 and line 9. Another modus ponens, and I get p. All right, cool. Now I actually have to have a thought in my head. Okay, now I have to remember what it is I'm trying to do, where I am in the derivation, what it is I'm trying to do. Okay, so what's the subderivation that I'm on? Where did I start my current subderivation? What line? Line 5. What kind of subderivation is it? It's an indirect derivation. So what am I trying to generate? Right. So what I'm looking for is a contradiction. I've got all this stuff. I've just been kind of deriving stuff to unlock resources for myself, to see what I've got. You know, easy peasy, like, okay, so I can just apply my rules to what I've got. Now I've got a bunch of stuff. Now I'm going to try to find a contradiction. So can anybody see a contradiction here? Yeah.
You have on line 10p and then on line 4 not p.
Exactly. Exactly. Line 10 is p. Line 4 is not p. This not p is outside my subderivation, right? But nonetheless, it's available to me. So I can say line 4 and then repeat to bring it into my subderivation. And line 10, and those two are my indirect derivation. Right? So I've generated a contradiction. By bringing not p into the subderivation where I've derived p, I've shown that if you assume y, you get a contradiction. That means that I've shown not y. Cancel and box. Box and cancel. Okay. Now, I'm not quite done, right? A couple more moves to make, but I'm making a lot of progress here, aren't I? So what I've got now is line 5 as an asset. I've got line 5. I've shown it. Keep in mind, all this stuff is within a boxed subderivation, so I'm not allowed to use any of this stuff anymore. I got this stuff by assuming something that I know is false, right? So you know you can't use it. I assumed y, but now I've shown that not y is true. So you can't use any of this stuff anymore. But I can use y, right? And what was I trying to do with y? Why was I trying to show not y again? Like, remind me. So for a conditional derivative, I was trying to show that if I assume not p, then I can derive not y. Right? So I did that. I assumed not P, and then from that I got that not Y is true. So what I've done on line 5, so you cite the show line where you did this. So on line 5, I managed a conditional derivation. Right? So I assumed it for conditional derivation, and I was trying to show the consequent. I did it. Hooray for me. So now I can box and cancel. So on line 5, I showed the thing. So I assumed, show me that if you assume not P, you get not Y. Did that. Now I've shown that if you assume not P, you get not Y. Well, why was I trying to do that again? Oh, geez. That's right. I had another conditional derivation. I was inside another conditional derivation where I assumed X and tried to show that on the basis of X, this thing follows. So now I can say on line 3, I've done conditional derivation. Cancel and box. Done. Okay. So this is, we're not yet doing mixed derivations that I mentioned a bit, but we're doing derivations that blend together indirect and direct. Right? So we've got an indirect derivation inside a conditional derivation inside a conditional derivation. Yeah? And we've seen like half of this. So we made it to line 13. It's a 13-line derivation. Half of it was just pure automatic moves. Pure moves that you just say, what am I trying to show? Oh, it's a conditional, so that means I do a conditional derivation. Right? And we unlocked all the resources, just doing those automatic moves. In this case, we unlocked all the resources that we need. So the strategy here was really just make the automatic moves, and then just a forward-looking, okay, now I've got some stuff that was unlocked from my automatic moves. I'm going to use that in whatever way I can, just sort of see what happens. And then we satisfied the thing that we were trying to do down here. So we generated our contradiction. That showed us that this conditional follows from, so this follows from assuming this. And that showed us that this follows from assuming this. Yeah? Okay. Easy, right? Okay. Yeah. Yeah.
Probably do it without SID.
You think you can do it without an indirect derivation?
Yeah, that's what I did. And like, if I can do that, it means it's correct.
Yeah. So if you correctly, so the question is, you know, if I can do this without assuming for indirect derivation, is that okay? Yeah, totally. If you can do it in a truth-preserving way, following exactly the rules. Yeah. So I think we've seen at least a couple of times, there are sometimes more than one way to get to the conclusion. And if they follow the rules, they're all exactly as good as each other. There's no points for using fewer lines. There's no extra points for like doing a beautiful, clean derivation. Just getting the answer is the answer. Sorry. Yeah. So yours first.
One example, you ever say like derive this with this specific derivation, or will you just say like
No. What I'll do is say derive this, and what I'll do is sometimes say using these rules. So we'll have a distinction introduced later on between basic rules and derived rules. So far, these are all basic rules. But so I'll list, you're allowed to use this rule, this rule, this rule, this rule to derive this. Yeah.
I was just wondering, if you find a contradiction within, here we found a contradiction in Y, but if you find it with like Z or Q, would that still be okay?
That's right. So if you within this indirect derivation, we didn't actually, so we found a contradiction by assuming Y, we got a contradiction between not P and P. Yeah?
But if you find like with other letters, that's okay, right?
Well,
So if you find like a contradiction with Z and Z.
you're trying to show not Y. So you don't get to cancel the not Y sign unless you've shown a contradiction by assuming this. But yeah, I don't think I understand the question actually. Okay, yeah, show me after. Okay. Okay. Should we do this one? Right. Now let's, okay. Okay, so quickly, mixed derivations. Sometimes you're going to be in a position where you think you want to start one kind of derivation, and you end up doing a different kind of derivation. And that's completely fine. So if you say assume for indirect derivation, but then you derived it directly, fine. Just say direct derivation, and you're done. Okay? So here's a quote from the textbook, and it's kind of bizarre. Like this kind of, it might take some energy to convince yourself that this is legitimate. But Parsons says the following: you may use direct derivation, conditional derivation, and indirect derivation to complete a derivation by boxing and canceling whenever they apply, whether or not an assumption has been made, and regardless of the type of assumption, if any. So anytime you generate a contradiction, you can say this line and this line contradict each other, indirect derivation, we're done that subderivation. Anytime you derive something directly, you can just say, yeah, I got it, direct, done. So if you're trying to show P, and you assume not P for indirect derivation, but that somehow you end up with P, you're done. You showed P, right? You're done. And it's okay that because you started one way and ended up another, that's fine. Can you see why that should be fine? Because you could have done the second, you could just add a couple more steps in here and say, look, line 2, line 12 are contradictory, therefore indirect derivation. It doesn't make a difference. Yeah? So that one should be fairly clear. Similarly, if you start a conditional derivation, but just directly derive the conditional you were aiming at, that's fine too. You just say direct derivation. You start a conditional derivation, you didn't show the consos, suppose you didn't end up showing Q, but somehow you ended up showing if P then Q, you're done. You're done. That's the thing that you were aiming at. And if you followed the rules to get there, then you followed the rules to get there, and you're done. Yeah?
So in that case, we're gonna have to cross or cancel the show line for number 3 or line 3.
Yeah, I think so. Yeah. Yeah. I don't think this will come up very often, but just that this is legitimate. And suppose you didn't start an indirect derivation, but you derive a contradiction, you're still done. This is the weird one. I think this is weird. Why is this weird? You're trying to show P, and what you showed is Q and not Q, something unrelated to P. Okay, why does that show that P is true? Well, it doesn't. It doesn't. It doesn't show that P is true. What it shows is that it's impossible for whatever the premise is for this. So it shows the argument is valid. And in this case, it's trivially valid. Remember the stuff about trivial validity. Validity is defined in terms of if the premises are true. So it's valid if it's impossible for the premises to be true and the conclusion to be false. If you derived a contradiction from the premises, then what you've shown is it's impossible for the premises to all be true. Right? So given if you derive line 11 and 12 here, following all the rules from the premises, you got some premises and you derive a contradiction straight from them without doing assume ID, and you derived a contradiction from those premises, what you've shown is those premises can't all be true at the same time. So that means the argument is automatically valid. It's trivially valid. And that's why it's okay to start with you're not starting with an indirect derivation, but you derived a contradiction, then your derivation's done. Yeah?
Why does a contradiction in indirect derivation show
So truth is the difference between truth and validity. It's the difference between truth and validity. So within a subderivation, if you assume for ID the opposite of what you're looking to show, and you derive a contradiction, that means that that assumption cannot be true, right? In this case, we're not showing that P is true. We're showing it's impossible for P to be true, P to be false while the premises are true, by showing that it's impossible for the premises to be true. Did that help? I feel like I say true and false so many. If you say it so many times, the words stop making any sense. Yeah, sorry. Yeah.
So, I'm confused. So as long as you prove something is false in indirect derivation, then it's valid?
Okay, so an indirect derivation, you're not showing that it's true, you're showing that there's a contradiction, right?
You can do that with any premise?
Well, do what?
Like, I think that was his question, like, can you do it with any letter, for example? So what we did was show not P.
Mm-hmm.
Okay, could you do it with not C or not Y, and it would be the same?
Oh, of course. So, yeah, I mean, if you show a contradiction between any two things that you have, the only thing about not C is that we're only using the letters P to Z.
Not Z, sorry. Z.
Z, so yeah, or C, but like, yeah. So you can do it with any, it doesn't have to be P, yes. Any of the letters, if you derive a contradiction between any two lines, then you've derived a contradiction, and you can either close off your indirect derivation, or in this case, you can just say, we're done. Because what you've shown, in this case, you haven't shown that P is true, you've shown that the argument is trivially valid. Yeah? By deriving a contradiction from the premises, you've guaranteed that it's impossible for the premises to be true and the conclusion is false. And that's all these derivations are showing. These derivations are demonstrating that these arguments are valid. If you derive the conclusion from the premises, that's one way of showing that the argument is valid. That's showing that it's non-trivially valid, that assuming the truth of the premises guarantees the truth of the conclusion. But given that we said that validity can also be trivial, you can also have trivial validity by showing that the premises cannot all be true at the same time. This is showing that the argument is valid in that picky technical way that we talked about validity. Yeah? Yeah?
So if we were to get this one of Julian test, that's the end of our word?
That's the end of, yeah.
We need to say that this is trivially valid and
No, you don't have to write anything else in. So if I might do.
But we end up with something that's not P, and then
But that's okay. That's okay. Yeah. So this is the kind of counterintuitive aspect of this, but it's nonetheless okay. With mixed derivations, doesn't matter how you started, so long as you satisfy. So this is what we've got here is a line 11 and 12. Satisfy the conditions for an indirect derivation. You generated a contradiction, and just because you started with a direct derivation or whatever you started with doesn't matter. You got a contradiction. That subderivation, or in this case the whole derivation, is done. You just say 11, 12, indirect derivation, cancel the show line and box it off, and you're done. Because what you've shown is that argument is trivially valid in this weird case. I might give you one of these on the test, just to sort of because we've talked about this, but
you said we can still cancel the show line.
you still cancel the show line. Yeah, you still cancel the show. You still do all the things that you normally do once you've demonstrated something. So you would cancel the show line, you draw the box around it, all of that. In any of these cases, you do that. Okay, I'm not going to try to teach you how to use show lines. Just extremely briefly, the very idea of writing yourself a show line. If you get stuck in a derivation, you can write a show line at any point, because a show line is not something you have to justify. It's just setting a goal for yourself. So you can say, I want to show this or that. And then you can start an indirect derivation, or you start a conditional derivation. This is a sort of the most This will be the more advanced derivation stuff. For the exercises this week, you don't have to generate your own, you don't have to think up your own show lines. But like in life, sometimes the goals that are relevant to you are not explicitly given to you. So all the examples that we've seen so far, the goals that are relevant to you, the show lines that you need to write, have been explicitly given to you. In your life, that's not always going to be true. Sometimes you have to come up with your own goals. So that's writing your own show lines when you haven't been prompted to do so. We'll deal with that kind of next week. This week, the exercises, you don't need to do that. If you master this skill, however, you've got all the tools that you need to do derivations like 1.001 to 1.030. So you can do the next, if you can figure out how to write your own show lines, you can do the next 30 derivations. Yeah. What's that? You're allowed at any point to open up a new show line, but you don't need. You'll only need to do the kinds of show lines I've shown you today to get through this week's exercises. Okay, thanks everyone.